Welcome to lesson 11 and power system analysis. In this lesson, we will be mainly reviewing whatever we have learnt on transmission lines. That is, basically we will be again going through the whole set of lessons that we did, that is from lesson 3 to lesson 10, and we will try to recapitulate whatever we have learnt in those lessons. In this lesson, we will start with introduction to transmission systems, then we will go to transmission line parameters, and then we will review what we have learnt on transmission line modeling, and finally on the steady state operation of the transmission line. So, we will start with an introduction to the transmission system. If you remember the earlier lessons, we talked about the different types of conductors that we use for transmission lines. We had said that the overhead transmission lines, which we will be dealing with mostly, use bare conductors, that is conductors which do not have any insulation on top of that, because they will be exposed to atmosphere and therefore, they can dissipate heat much faster, and so they can be worked at higher current levels. Now, the type of conductors that we use are normally copper conductors. Of course, copper being very expensive, nowadays copper is no longer being used, though this has a much higher conductivity as compared to the other materials that we use now. The conductor which is now very much in use, in fact almost 90% of the conductors which are used for overhead transmission systems are ACSR conductors, that is aluminum conductor steel reinforced. These conductors are made up of small aluminum conductor filaments which are twisted together, and since aluminum does not have very large tensile strength, so to provide the tensile strength or the mechanical strength to the conductor system, steel wires are used for as a reinforcement. So, what we have is the central core is made up of a number of steel wire or steel filaments, and on top of that we have the aluminum filaments which make the whole conductor. We can see this in this diagram, where we have the inner core made up of steel strands, and on top of that we have these filaments of aluminum conductor, or the strands made up of these aluminum conductors. So, this is how ACSR conductor looks if you take a cross section of the ACSR conductors. The other conductors which are not so much in use, but have been used in some places, are all aluminum alloy conductors. These conductors again are made up of aluminum alloy, so that it gives more mechanical strength to the aluminum conductor. We sometimes use aluminum clad steel conductors, that is, we have steel conductor core on that aluminum conductor is cladded. So, aluminum clad steel conductors are also used, but these are not so much in use. A new type of conductors which are now being used in extra high voltage lines sometimes is what we call expanded ACSR. It is the same ACSR, or the aluminum conductor steel reinforced conductor, except that between the steel core and the aluminum we have some fibrous material which is placed in between. This is the filler material which is introduced there just to increase the diameter of the conductor, as we have seen already, the inductance of the conductor will reduce if its diameter increases, and therefore, this is sometimes used to reduce the inductance of the conductor. So, expanded ACSR conductors are being used in some places. It is very similar to the ACSR, except that here in this position we will have some filler material which will be put in, so that the overall diameter of this conductor is increased somewhat. Then comes the support structures on which these conductors are put. These are basically transmission towers or transmission poles. Now, here we have shown transmission towers. This is for extra high voltage lines. Generally, what you have is these 3 phase conductors are placed like this. At a lower voltage, this can be made like this also. Here, the configuration of the conductors are in a horizontal plane, and 3 phase conductors are placed like this. Here at the top, these red ones can be seen, and these are what we call the ground wires or the earth wires. These wires are directly connected to the tower, and through the tower footing resistance they are grounded. So, these are mainly there to protect the phase conductors from direct lightning stroke, because these provide much low resistance path to the lightning current than what will come through this phase conductors, and therefore, lightning will rather directly, if it strikes directly, it will strike these ground wires which are much above the phase conductors and will be grounded. Instead of horizontal configuration of the conductors, we sometimes use vertical spacing also. So, for that we have tower structures which are shown here like this, where this tower is showing a double circuit line. One circuit is here, A, B, C, the 3 phase conductors of one circuit, and A dash, B dash, C dash, the 3 phase conductors for the other circuits. Both the circuits are running parallelly to each other, and they are placed on the same tower. Again, putting A and A dash like this, B, B dash like this, C and C dash like this is done mainly because this helps in reducing the overall inductance of the circuit. Sometimes, when the load is not very high and the load may build up later, what we do is we use a tower construction which is very similar to a double circuit tower construction, but what we do is we use only 3 arms like this, and we place our conductors A, B and C like this, and when the load builds up, the other arms will be added and we will get a double circuit 3 phase line like this. So, this is about the support structure or the transmission towers. Next, we come to the electrical parameters of the transmission line. As we know, the transmission line are consisting of conductors. These conductors will have some amount of resistance. So, the transmission line will have resistance. Since these conductors will be carrying current, magnetic field will be built up because of the current flowing in the conductors, and these magnetic field will interact with the other conductors which are carrying current, and therefore, we will have some inductance involved. So, we have inductance on the transmission line. Since these conductors or the overhead lines are at high voltage, So, there is a voltage difference between the two phase conductors as well as between the phase conductors and the ground. Since there is a voltage difference and there is insulation in between, which is normally air for overhead conductors. So, we will have some capacitance also involved. So, transmission line will have 3 electrical parameters: resistance, inductance and capacitance. Resistance and inductance will be in series, whereas the capacitance will be between the line and the ground or between the two lines. So, this will be coming as a shunt or a parallel connection. So, we have series impedance of the line given by resistance and inductance and the shunt admittance of the line given by the capacitance, which is coming between the line and the earth or the neutral. Now, for calculating the resistance, we all know resistance, the DC resistance at any temperature R DC at temperature T is given by rho at that temperature, that is the resistivity of the material of the conductor at that given temperature into L, the length of the line or the length of the conductor, and A, the cross sectional area of the conductor. So, it is rho L by A and the unit for resistance is ohms. Now, conductor resistance will depend on some other factors as well. These factors are, since we are using stranded conductors and these conductors are spiraled. So, because of spiraling, what happens is the length, the effective length of the conductor gets reduced. So, the actual length of the each filament will be much longer compared to the effective length of the conductor. This is because when we twist the conductors, the conductor each strand of the conductor length will be larger than the final conductor length, which comes out by making this twisting for all the conductors. So, spiraling, because it increases the length of, that is because it uses a larger length of conductor than the actual length of the line. Therefore, the effective resistance of the line will be somewhat larger than what we will calculate by taking the line length. So, this is mainly because this L here, actual L, will be larger than the line length. Similarly, temperature, as we have seen, this resistivity of the conductor will increase with the increase in temperature, and therefore, when the conductor is carrying more current, the heat dissipation is going to be more, I square R losses are going to be more, which will be dissipated as heat, and therefore, the conductor temperature will go up, and this will increase the resistance of the conductor. Another important factor is the frequency. In alternating current, what we have is the current and voltage is going through a cycle a number of times every second, like for 50 hertz, the current and voltage waves go through 50 cycles per second. Now, because of these changing of the current, the magnetic field also gets changed, and therefore, since this magnetic field is changing and it is cutting a conductor, therefore, some inductance is getting induced. So, what actually happens because of this frequency is that the lower or the central part of the conductor, if you look at this conductor, what we will see is the inner part of the conductor will be experiencing more flux linkages, and therefore, the inductance of these will be, these strands will be more than the inductance of these strands, and therefore, and AC current will see a more reactance or the more impedance for to its flow, and therefore, less and less current will flow through the core and more current will flow through the outer edge of the conductor or the strands at the outer edge of the conductor, because here the flux linkages will be lower and the inductance seen will be less, and therefore, what we find is more current will flow through this part and less current will flow through the central part. This is what happens, and that is since this appears as if the current is trying to flow through the outer skin of the conductor. Therefore, this effect is called skin effect. So, because of the frequency, we have this skin effect. Higher the frequency, more and more current will be flowing through the outer edge of the conductor, that is, more current will be flowing through the skin, and less the frequency, the current distribution over the cross sectional area is going to be more uniform. So, higher frequencies will make the current distribution over the cross sectional area non-uniform, with more currents flowing through the edge and less flowing through the central part of the core. Well, as we have seen, the resistance depends on resistivity and resistivity depends on the temperature. The resistivity of conductor metal varies linearly over normal operating temperatures according to relationship rho T2 is equal to rho at T1 into T2 plus T divided by T1 plus T, where this T is a temperature constant which has different values for different materials. So, if we know the resistivity at some temperature T1, we can find out the resistivity at another temperature T2. As we have seen, the resistance of a conductor depends on different factors such as spiraling, the temperature and skin effect. Therefore, to get the actual or the effective resistance of a conductor under which is working under alternating current system, we do this by experimentally finding out the resistance by finding out the loss in the conductor, and therefore, finding out resistance as loss divided by I square, because we know I square R is the loss which takes place in the conductor. So, using experiment where we flow a certain amount of current through the conductor and find out the loss in the conductor, we can calculate the AC resistance of the conductor. However, if we calculate the AC resistance DC resistance of the conductor for at 50 hertz or so, most of the time due to the spiraling, skin effect and other effects, if we take them into consideration, the AC resistance will be about 4 to 5% higher than the DC resistance. Next, we will talk about the inductance. We had seen that we can calculate the inductance of overhead conductor using the following steps. First, we calculate the magnetic field intensity H using Ampere's law. Then we calculate magnetic flux density B is equal to mu H. So, once we have calculated H, knowing mu in case of non-magnetic conductors like aluminum or copper, mu is same as mu 0, that is 4 pi into 10 to the power minus 7. So, using that we can calculate the flux density, and from flux density we can calculate the flux and the flux linkages, and then we can calculate inductance from the flux linkages by L is equal to lambda by I, flux linkage per unit current. Now, if we take up a solid conductor, here what we find is when a current is flowing through this conductor, it is going to set up magnetic field inside the conductor also. So, here in this diagram at a distance x from the center, we have a magnetic field with intensity H x, and this field is going to link only this part of the current which is inside, not the current outside, whereas this current will also set up magnetic field outside the conductor, and this will be linking all the current in the flowing in the conductor, because it will be enclosing the full conductor. And therefore, we can find out the total inductance by finding out the flux linkages which are internal and the flux linkages which are external, and this we can see that at any point p up to at any point p at a distance d from the center of the conductor, the total flux linkage will be given by 2 into 10 to the power minus 7 into I multiplied by log n e to the power 1 by 4 plus log n d by r. This log n e to the power 1 by 4 term is coming out because of the internal flux linkages, and we see this is independent of the radius of the conductor, whereas this term is coming out because of the external flux linkages. The point P is at a distance d from the conductor and r is the radius of the conductor. So, if we combine these terms, then we can write this as 2 into 10 to the power minus 7 I log n d divided by e to the power minus 1 by 4, that is, we took negative here and we have put it in the denominator. So, e to the power minus 1 by 4 into r, which we can write as 2 into 10 to the power minus 7 I log n d by r dash, where r dash is equal to e to the power minus 1 by 4 r, or equal to 0.7788 r, which tells us that due to internal flux linkages, the effective radius of the conductor gets reduced somewhat, that is, from r it becomes about 0.7788 r, or 78% of the actual radius of the conductor. So, once we know the flux linkage, we can calculate the inductance of the conductor for flux linking up to point P. So, that is lambda P by I. So, this is equal to 2 into 10 to the power minus 7 log n d by r dash henries per meter. Now, we have seen that normally the conductor that we use is not a single solid conductor, but is made up of a large number of strands of conductor. So, here we are trying to depict that condition as a general case, where a conductor X is made up of n number of strands, and each strand is having a radius r x. This we have said that is, we have made an assumption that all strands are of the same radius. This is normally true, and each conductor or each strand of this conductor will be carrying 1 by n of the current, because they are having equal cross sectional area of the same material. So, they will be carrying 1 by n of the current, that is, there are n subconductors. So, and total current flowing through this is I. So, each subconductor will be carrying I by n current. The other conductor, which is a return conductor, consists of m number of subconductors, and each one of them will be carrying minus I by m current, because this is a return conductor. So, current I is flowing through this conductor and returning back from the other conductor. So, conductor Y has m subconductors, each carrying I by m current. These are depicted as 1 dash, 2 dash, 3 dash up to m, and r y is the radius of each subconductor. The distance of any subconductor to other subconductor is denoted by, like from subconductor 1 to subconductor k in conductor x, it is d k 1, and from subconductor k in x, conductor x, to subconductor 1 dash in conductor set y, it is d k 1 dash. So, with these we can now again find out the flux linkage of the conductors of all the subconductors in conductor x. That will come out to be 2 into 10 to the power minus 7 into I into log n multiplication from k is equal to 1 to n of multiplication m is equal to 1 dash to m of d k m, that is distances from subconductor k to subconductor m, to the power 1 by n m, and this will be divided by multiplication m is equal to 1 to n into for d k m, that is from conductor k to m, and this will be to the power 1 by n square. This is what we will get after finding out the flux linkage for each subconductor and then adding them up for all the subconductors. Therefore, the inductance of this conductor x will come out to be 2 into 10 to the power minus 7 log n dxy by dxx, where we are writing dxy as m nth root of product k is equal to 1 to n product m is equal to 1 dash to m dkm. That is, what we are saying is that this is the geometric mean distance of each subconductor in conductor x to each subconductor in conductor y for all the subconductors in conductor x, and dxx is again the geometric mean of the distance of each subconductor to other subconductor in conductor x. So, this is what we call as GMR, or the geometric mean radius for the conductor x, and GMD is the geometric mean distance between the two conductors x and y. Therefore, similarly we can write for inductance for conductor y as equal to 2 into 10 to the power minus 7 log n dxy by dyy henries per meter per conductor, where dyy will be the geometric mean radius of the subconductors in conductor y. That is, for each subconductor to all the subconductors in conductor y, we will find out the geometric mean distance, and that is what we call as the GMR or the self GMD for that conductor, and the total inductance will be sum of the inductance for conductor x and conductor y, because both these are in series. Now, for a 3-phase system, what we have seen is that if we put the 3 conductors in a symmetrical spacing, that is on the vertices of an equilateral triangle, then all the 3 conductors will have same flux linkages because of the symmetry of their position. But this is not feasible practically when we are putting the conductors on transmission towers, because this will make our right of way much larger and transmission tower design will also be more expensive. So, we have seen that we either put them in some kind of a vertical configuration, or maybe horizontal configuration, or somewhat skewed configuration as such. In that case, since the 3 conductors will not have the same symmetrical physical position. So, the flux linkages of the 3 conductors will not be same, which means that the inductance of the 3 conductors will not be same. In that case, what happens is the transmission system will be an unbalanced system. We will have different values of inductances and so reactance for each phase, and therefore, with the same current flowing in them, we are going to get different voltage drops, or at the other end of the transmission line the voltage phase will not be symmetrical, and we will have an unbalanced system. In order to avoid this kind of a situation, what we do is we transpose the transmission line. That is, what we do is we make all the 3 phase conductors to go through all the 3 positions as shown in this figure. The conductor of phase A goes through this position for 1/3 length of the line, goes through the position of B for the other 1/3 of the line, that is second 1/3 portion of the line, and goes through the position of conductor C for the last 1/3 portion of the line. Similarly, the conductor of phase B goes through this position for 1/3, goes through position of C for the next 1/3, and goes through the position of A for the next 1/3, and so on. Thereby, each conductor or each phase conductor goes through all the 3 positions, and therefore, the average flux linkage of each phase conductor will be same, and thereby the inductance for all the 3 phases are going to be same. This way, we try to make a symmetry and balance for the 3 phase conductors inductance. So, here if we use this transpose system, then we have inductance of any phase. Here we are writing for phase A, inductance L A is equal to lambda A by I A, which is equal to 2 into 10 to the power minus 7 log n cube root of d 12, d 23 and d 31. This is happening because we are having all the 3 positions for each conductor. So, we have got this cube root of d 12 d into d 23 into d 31 divided by d s, where d s is the GMR of the conductor, and this cube root of d 12, d 23 and d 31 is called the equivalent distance DEQ, and therefore, we can write L A is equal to 2 into 10 to the power minus 7 log n DEQ by ds, where this DEQ or the equivalent distance between the phase conductors is like saying that this is the equivalent equilateral distance between the 3 phase conductors. That is, if we would have made equilateral distance for the phase conductors for the 3 phase conductors, then we would have had this distance between them. Now, if we see the relationship of inductance, we find that the self GMD or the GMR for the conductor is coming in the denominator, and therefore, if we can increase this value, then we can reduce the inductance and therefore, the reactance of the transmission line. We can reduce the reactance also by reducing dq, that is the distance between the phase conductors, but this is not feasible because we have to maintain a certain minimum distance between the conductors because of the high voltage which is there between the 2 conductors. We also have to take into account that there will be wind blowing, and because of which the conductors will be swinging with respect to each other, and therefore, the minimum distance between the conductors must be maintained, otherwise there can be a flashover between the conductors if the insulation between them breaks down. So, for increasing the effective radius or the self GMD or GMR, whatever we call it, we many times use bundle conductor. Another advantage of using bundle conductor is that it reduces the electric field strength on the conductor surface. That is, now what we have is, if we would have used one conductor with the same cross sectional area, if we divide that into two conductors, then the surface area of these two conductors together is going to be large, and therefore larger, and therefore electric field strength on the conductor surface will get reduced for the same potential. Now, these conductors, which are connected by means of spacers, which are conducting material. So, this is called a configuration for bundle conductor. Here we have two conductors together, that is conductor 1 here and conductor another here with a distance d between them. Here we are showing the configuration with three conductors 1, 2, 3 with spacing d between each one of them, and this one shows 4 conductor. In fact, the higher the voltage, we use larger number of subconductors in a bundle. This reduces the electric field strength considerably, and therefore, it reduces the corona discharge and corona losses and the associated radio interference and audible noise with it. As we have also seen, by using the bundle conductors, what we have done is we have also increased the effective GMR of the conductor as such. If we are using two conductors, then the self distance or the effective GMR will be given by 4th root of r dash into d whole square, because this its own distance with this conductor will be r dash, its distance with the other conductor is d, then for this conductor its own distance is r dash, and the distance of this conductor with this is going to be d. So, we have r dash into d into d, that is, and we take the 4th root of that. So, we have got the 4th root of r dash into d square, which comes out to be square root of r dash d. Now, this d will be normally around 40 centimeter to 45 centimeter, or about 10 times the radius of the subconductor, and therefore, this square root of r dash d is going to be much larger than r dash. Same thing we can see for this 3 conductor bundle or for 4 conductor bundle. We find that for 3 conductor bundle it is cube root of r dash d square, and for 4 conductor bundle it is 1.091 into 4th root of r dash d cube. And for bundle conductor, we replace the r dash by this ds, that is the self distance or the GMR of the conductor as calculated here. Now, once we have calculated the inductance and the resistance, we have found out the series impedance of the line per unit length. Now, since we know that the conductors are at high voltage, there is a voltage between the two phase conductors and there is a voltage between the conductor and the ground, we have a capacitance involved and we can calculate that capacitance again by using the Gauss's law. So, using Gauss's law we find out the electric field strength, and then from that we can find out the voltage between the conductors, and then we can find out the capacitance C is equal to Q by V, where Q is the charge on the conductor. So, we can calculate the capacitance. The capacitance to ground or capacitance to neutral for any conductor in overhead system will be given by Q A by V A n, which on calculation comes out to be twice pi epsilon log n d by r, where epsilon is the permittivity of the material. In this case it is for overhead lines, this is the permittivity of air. So, this C A n is given by twice pi epsilon log n d e q by d s for a 3 phase system, where d e q is the equivalent equilateral distance for a transposed line. And if we are using bundle conductor, we have to replace this d s by the effective GMR or the self GMD of the bundle conductor system. Now, since we are putting these conductors on towers and the distance between the phase conductors normally for a 220 kV line will be of the order of around 10 meters, as well as the distance of or the height of the conductor from ground, that is the minimum clearance that is required, is also of the same order. Therefore, we need to consider also the effect of earth when we are calculating the capacitance, because the height of the conductor or the distance from earth of the conductor is of the same order as the distance between the phase conductors. Now, earth can be seen as an equipotential surface, that is a surface where potential is equal. It is normally the ground potential or the zero potential that we have, and to take this into effect, what we have to do is we use what we call as a method of images. That is, what we do is we consider image conductors below the ground at a depth equal to the height of the overhead conductor above the ground, and this image conductor has opposite charge. In fact, if we look at the electric field contour, when we have a conductor placed above the ground, this conductor has a positive potential. Therefore, the field lines will look like this. Now, the earth being an equipotential surface, these lines will be coming to the earth at 90 degrees or perpendicular to the ground. Now, this situation can be given or can be made by considering an image conductor with negative charge at a distance h below the ground, because if we put this image conductor here like this, then the field lines will look like this. Now, we see this field lines configuration is same as if the ground was there. So, now even if we remove the ground with this image conductor placed here, the field line configuration does not change, or the effect of capacitance will not be changed. So, for taking this effect of earth into consideration, what we do is we place an image conductor below the ground at a height equal to the height of the conductor above the ground, and we put the image conductor with the opposite polarity. For a 3-phase system, we have shown here we have phase conductor A, phase conductor B and phase conductor C. Q A is the charge on that, Q B is the charge on phase B conductor, Q C is the charge on phase C conductor. We have taken this height to be h, then we have taken image conductor for A with a charge minus Q A, and the height h 11 will be equal to twice h. Similarly, for B we have image conductor here, and C we have image conductor here, and we have all these distances given from conductor to image conductors as well as between the conductors. And if we use this configuration, then this earth effect is taken into account. So, whether this is here or it is not here, it does not matter, and with these 6 conductors now we need to find out the capacitance. If we do this calculation, then we find that the capacitance to neutral for any of the phase conductors will be given by twice pi epsilon divided by log n dEq by ds minus log n cube root of h 12 into h 23 into h 31 divided by cube root of h 11 into h 22 into h 33. Now, what we are seeing is the effect of ground is to introduce this term in the denominator, that is, the denominator is getting reduced by this amount, and therefore, the capacitance is somewhat increased. So, effect of earth is to increase the capacitance somewhat. Now, this term h 12, h 23 and h 31 and h 11, h 22, h 33, if the height of the conductor is much above the ground, then these terms will be almost equal and this effect will be negligible. Next, we will, now that we have calculated the resistance, the inductance and the capacitance, next comes how to model the transmission line. Now, we have seen that we are having resistance per unit length of the line, we have inductance per unit length of the line, and we have a capacitance per unit length of the line that we have calculated. Here I have shown also a conductance, which most of the time we neglect. This is any current which is flowing, any leakage current which flows across the insulators of the line, which is normally very small and is most of the time neglected. So, we have a model of the transmission line where we have resistance and inductance per unit length of the line and a capacitance per unit length of the line. So, we will have basically a distributed parameter model of the transmission line, that is this series the resistance and inductance are in series and the capacitance is in the shunt, and this will be there for per unit length of the line. Now, this model, if we use in detail, leads to somewhat complicated mathematical model and complex for calculation. So, most of the time we try to use simpler equivalent models. For any of these line configuration, this line if we see here we have voltage and here we have voltage at the other end, we have resistance, inductance and capacitance involved in between. So, we have one port here of 2 terminals and one port here of the 2 terminals. We have voltages at this end, we have voltages at this port, we have current flowing at this port and current into this port. So, we can represent this transmission line as a two port network, where we have at the sending end voltage V s and the current I s. At the receiving end we have current I r and the voltage V r. Now, this can be represented as V s is equal to A V r plus B I r volts and I s is equal to C V r plus D I r. That is, we can represent this two port network in terms of ABCD parameters. We can write this as V s I s is equal to ABCD V r I r, and one of the property of this ABCD parameter is AD minus BC is equal to 1. Now, as I said earlier, we do not use the full distributed parameter model for the transmission line most of the time. In fact, if the line length is less than 80 kilometers, then we can make a much simpler model of the transmission line. Normally, these lines will be low voltage lines, and therefore, the effect of the charging current or the capacitance of the line can be neglected. In that case, the line will have only series resistance and inductance, and we can lump all these resistance and inductance into single resistance and inductance for the whole length of the line. So, we have a lumped parameter model, where we have only series impedance of the line, which is Z will be equal to Z into L. Small z is the series impedance per unit length of the line, L is the length of the line. This is equal to R plus j omega L, where R is the resistance per unit length of the line and L is the inductance per unit length of the line, multiplied by L. So, this is a model which is a very simple model, but this can be used only for short length lines, that is lines which has length less than 80 kilometers. Otherwise, the errors which will creep will be significant. In case the line length is somewhat more than 80 kilometers, but less than 250 kilometers, we call these lines as medium length lines. Since these lines will generally be high voltage lines, we can no longer afford to neglect the capacitive part of the model, that is, the charging current is going to be significant and it needs to be modeled, and therefore, we have to have the capacitance of the line included in the model. What here we do is, normally we use a pi model, where we lump the total series impedance into a single series impedance for the whole length of the line, and we lump also all the capacitance of the line, that is, if we have calculated the capacitance per unit length, multiply it by the total length, then we get the total charging capacitance of the line. We divide this total charging capacitance into two parts and put them the half on one, that is receiving end, and half at the other end, that is the sending end. So, half of it is put at the sending end and half of it is put at the other end, the receiving end, and this leads to a nominal pi circuit for the medium length line. For this line, if we do the ABCD parameters, then we have V s I s is equal to 1 plus y z by 2 z in y into 1 plus y z by 4, 1 plus y z by 2 V r I r. A is 1 plus y z by 2, B is z, C is y into 1 plus y z by 4, and D is equal to 1 plus y z by 2, that is A is equal to D. And if we do again A D minus B C, we will find that it is equal to 1. Now, when we take the long line model, we will have to use distributed parameter models, that is, for lines lengths greater than 250 kilometers, we can no longer afford to lump all the series impedance and the shunt admittances. We will have to use distributed parameter model for the long line. Now, when we do that, then we can again make the ABCD parameters for this line, and here what we find is the ABCD parameters will be given by at for any distance x, we can calculate this. If we put x is equal to L, then we have for the whole length of the line. So, A is equal to D is equal to cos hyperbolic gamma L, B is equal to Z c sin hyperbolic gamma L, and C is equal to 1 by Z c sin hyperbolic gamma L, where Z c is given by Z c is given by root over Z by Y, where Z is the series impedance per unit length of the line and Y is the shunt admittance per unit length of the line, and gamma is given by root Z into Y. So, by substituting those values, we can calculate ABCD parameters. Only thing here we see is we have hyperbolic functions involved in this case, and the computation is somewhat cumbersome. So, with this we stop today, and we will continue with this review in the next lesson. Thank you. Welcome to lesson 12 on power system analysis. In this lesson, we will discuss modeling of transformers. Well, this lesson we will start with introduction of transformers, then concept of an ideal transformer, then we will go into physical transformers and their equivalent circuit. After that, we will talk about 3-phase transformers and 3-winding transformers. Well, the main objective of this lesson is to explain the concept of an ideal transformer. That is, once you are through this lesson, then you should be able to explain the concept of ideal transformer, develop the equation or the equivalent circuits models for single phase transformers, then 3-phase transformers and 3-winding transformers.